Okay, so for our next speaker, we'll have Yuval Tassa, who is a researcher at Google DeepMind and working on MuJoCo. And I think he will share quite a different view on differentiable optimization.
I don't know if they're different. All right. So I'm going to talk a little bit about MuJoCo, then quite a bit about a tool called MJPC, and I'll tell you how we do derivatives there. And then I'll have maybe a few general thoughts about MPC and about derivatives, whether we want them at all. I changed my title a little bit. So use finite differencing if you really need derivatives, but do you? Okay. So first, a little bit about MuJoCo. Why do you not see any videos? Maybe I need to do this. What happened to the video? Ah, here's a video. Okay. I hope everybody here knows a little bit about MuJoCo. It was written by Emo, who's maybe somewhere in the room. There he is. A little bit of help from me and Tom. And MuJoCo is made for model-based control, and it's a very good tool for it, and we'll see soon why. In 2021, DeepMind acquired and open-sourced MuJoCo. We've added a lot of features since then. On the top right, you can see this cool fluid dynamics that we added in order to model fruit flies flying. And we have this thing called the MuJoCo Menagerie, where we have lots of robots. Some are well identified, most not so much, because nobody knows how to do sysid. One day I will teach you. It's very easy. We now also have a GPU branch called MJX, and I'll show you things from MJX soon. These are some reasons why MuJoCo is good for control. It has a very powerful feature, which is analytical inverse dynamics in the presence of contacts. Maybe Emma will talk about that a little bit. We have partially implemented derivatives, but really smoothness is more important than differentiability in the computational sense. I'll talk about that a little bit later. So contacts in MuJoCo can be made smooth if you like. It's part of the contact model. MuJoCo is very fast. I think the numbers are actually better now. We're not very good at keeping up, at redoing the benchmarking every time we speed it up, but that's already pretty fast. And now I want to talk about this tool called MJPC. It was written by Taylor Howell in the summer of 2022. He's now part of the team. At the time, he was an intern. The goal of MJPC is to be a playground for predictive control. It was written very quickly by someone who was not very familiar with MuJoCo, so it's also a testament to how easy it is to write such applications in MuJoCo. This is an application. Simulation and planning are completely asynchronous. I'll explain in a bit what that means. But mostly, you don't need a fast computer in order to run it. The GUI is probably the most important thing. You can tweak everything. You can change the horizon. You can change the planner. We have quite a few shooting methods for planning, but one could also implement direct methods. And of course, it's fully open source. The problem setup is the standard discrete time predictive control setup, discrete time dynamics. You've got a running cost. You minimize the sum of the costs. Generally, the two classes of optimization are direct, which also optimize over states, or shooting, which only optimize over controls. Currently, we use shooting because we like it, but one could use direct methods. The asynchronicity is the key thing here. So this is a general confusion that people have. People think that the planner needs to replan at basically at the control rate. That's not the case. The planner can plan much more slowly, because you can keep reading from the old plan until you get a new plan. You can do this asynchronously, and it works beautifully. So the planner can, can optimize in 10, 20, 30, 40 milliseconds, even if your controller is at 5 kilohertz. It's fine. The task structure that we use is quite, I don't know if it's standard by now, but I think it's quite relevant for this talk. I'm going to talk about this in a bit. But you see the top right is basically the cost structure. So the cost is a weighted sum of norms of residuals. Norms are simple functions that are convex, and we need to know their gradient and Hessian. Think quadratic, nothing very fancy. The residual is the interesting thing. So the residual is what the user needs to define, and he writes it with a short piece of C code, and Mujoko implements it as a user sensor. And the important thing in the context of this talk is that because finite differences, which is what we use for the dynamics derivatives, scale like the inputs, you can add whatever you want to the outputs, and you get those Jacobians for free. Does that make sense? Good. We don't do second-order derivatives of the dynamics. Nobody needs that. Gauss-Newton is enough. So now let me explain why we do finite differencing, and then I'll tell you how to do it. So finite differencing is, usually people think of it as, oh, it's the lazy person's approach to derivatives, and that's true. But laziness is a good thing, okay? Making people's life easy is a feature, is not a bug. I was talking, is Nicolas here? I was talking to Nicolas yesterday about some trick we use in our integrators in Mujoko, and he said, oh, that's very simple, but now I need to write it in the derivatives. Like thinking about how you need to change the derivatives whenever you change the main code, if you write your derivatives manually, it's a huge pain in the ass. But unfortunately, there is, of course, auto-diff packages, but auto-diff packages are generally, almost all of them are initially designed for neural networks. They're not meant to to work in real time. Hooking up auto-diff generated code to something that runs in real time is really hard and painful. So it's just easy. Another thing is parallelizability. And this is something also a lot of people don't understand. Of course, everybody trivially understands that the nudges can be parallelized, right? You're nudging some vector, so all of those can be parallelized, but that's actually not where the real benefit is. The real benefit is parallelizing across a trajectory, right? So we do a rollout of a whole trajectory. That's a serial operation, but now getting the derivatives on each time step is something you can do in parallel on multiple threads. It's very coarse-grained because each thread does the entire finite differencing loop. So it's a very high efficiency parallelization. And importantly, this is not something that you're going to get from autodiff, right? Because when you do autodiff, it's like a forward and a backward. So then you have to be like the derivatives become serial by the very nature of how autodiff works, right? So this approach of computing all the derivatives in parallel, and then the backward pass is basically, matmols, because you computed the Jacobians along the trajectory. It's much more efficient. And of course, finite differences generalize to things that are not finite differences, right? Unscented Kalman filters, all sorts of rich types of, right? I don't have to nudge exactly in one direction. There's all sorts of ways of generalizing finite differences in ways that are quite interesting. And finally, surprisingly enough, finite differences can be extremely fast if you know what you're doing. And there's like 2 or 3 tricks that you need to know, and they'll just be much faster than you think. So here's this is one slide, how to finite difference. Step 1, use double precision. Okay, don't try this with floats. I mean, you can, it might work, but then things will suddenly be strange and you won't understand why. Second, this is also true for any kind of, don't differentiate things that are not continuous. Bad idea, just don't do it. So in Mujoko, it's very easy. A a bit like what we saw in the previous talk in Mujoko. It's very easy to make all the contacts differentiable, stiff, but differentiable. It's basically a parameter that you need to tune, so tune that. A question that people love to ask when I tell them that we use finite differences, they say, oh, how do I choose the epsilon? It's so hard. It's not hard. It's not hard. There's a huge range. All of these epsilons work. Just use 1e minus 6, you'll be fine. It's fine. It'll work. Double precision is fine. Just use 1e minus 6. It works. Okay, so here are the tricks to making it fast. One is recompute only what you need. Right? So when you're finite differencing, you have a point in the middle and then like you nudge it in various directions. So depending on what you're nudging, don't recompute everything. If you're nudging forces or controls, you don't need to recompute positions and velocities. If you're nudging velocities, you don't need to recompute positions. If you're nudging positions, you need to recompute them. And even more valuable is worm starter solver, right? All, physics, all interesting physics simulators have some kind of iterative solver inside them. And of course, we all know if you're very clever, you can get from the KKT conditions, you can get the analytical derivatives through the inverse. Yes, but even easier, just warm start the solver and reduce the iterations. So in MJPC, we reduce the number of it, like you compute the first one in the forward pass, you already did it. Then you set the number of iterations to 1, and then you nudge, and then everything is 2.5 times faster. Because instead of doing all the iterations again, you just do 1 and it's enough because it's Newton, so it converges well. And this gives you really, really fast fin-diff or derivatives. And you can do all of this in like 2 days. Okay, so even if you want your analytical derivative, always have this at hand because this will always work. All right. Now let me show you a little bit about MAPC, the actual software. So here I'm showing you some of the knobs. So I turned the planner on, and now I can change the goal. So these are all the usual benefits, right? The usual benefits and to some extent trade-offs of MPC. You can change everything, right? So now I'm changing the goal, nothing happens. I'm increasing the weights again, and it will restabilize. We all understand this, right? In MPC, because nothing is learned, raw MPC, here like a bunch of shooting methods. When we launched this, we only had 3. Now we have lots. So this is LQG. This is gradient descent, just plain old gradient descent on the controls. And most interestingly, this sampling-based thing. So let's talk a little bit about, and now we have lots more, CEM and PPI, all sorts of things. Before I talk about that, let me explain the asynchronous thing in case somebody didn't get it, because it's really valuable. So what you're seeing here is I'm slowing down. Let's go back to the beginning. This quadruped tries to get over the hill. It cannot get over the hill, so I slow down the simulation. The planner has more time to think, and it figures out how to get over the hill. So this asynchrony, this live asynchrony is incredibly valuable when tuning your cost functions. And in particular, you don't need a fast computer. And usually when I gave this talk, at the end of the talk, I would give a live demo on my laptop. Now we have a new policy. I will give a live demo on your laptop. Okay? So at the next break, if you bring me a laptop, Mac or Linux, we don't support Windows, sorry. I will install this on your laptop and you'll get to do this on your laptop. So when you do LQG, you have to use the raw control sequence because of the Bellman principle. But for other planners, in particular the sampling-based planners, you can use a reduced search space. You could probably also just smooth the actions, but this is nice because it's like saves memory. And we found this to be quite beneficial to represent your actions with splines. And here's like a quick video summary. This is from 2 years ago, so I might, how long is this? I might go through this quite quickly. I think I'm good. So I just want to show you a few features of the software. Here I'm changing. So obviously, so here is the sampling planner, and you can see the plans. We saw this in Dr. Park's talk before. It's very convenient. You can perturb it, obviously, while it's walking, and it will get up, and etc., etc. It's a lot of fun. Now we can make it like walk very small. What is this? LQG. I'm switching planners here. So this is like one of the lessons. I'm going to talk about this in a bit. Basically, gradients are good for smooth problems. If your problem is smooth like this, or locomotion, which in a sense is smooth the moment you make contact with the floor, gradients are great. But for difficult problems, and I'm going to show you some really tricky manipulation problems in a bit, gradients just don't cut it. Like, unless you have some prior that tells you, how do you make, you need to first make contact before you have the gradient. It's not really tractable. So I'm going to talk about that a little bit. Like, we're now, the issue is that derivative-based methods are just much more efficient. So I'm still waiting for the best of both worlds method, right? Something that will use sampling, but give you the efficiency of Newton steps. And I think somebody will find it. It's not, shouldn't be that hard. Maybe. Let's see. Okay, some more perturbations. Okay, this is less interesting because it's from two. Let me just, this is cute because I want to go fast. This is the hardest problem that we did 2 years ago, and we were so surprised that it worked. Like, we didn't think that this sampling thing would work at all. So what you're seeing here is just pure random. Well, I'll talk a little bit more about what we mean by predictive sampling, but it's a non-algorithm. It's just do some rollouts, pick the best one. But look what it's solving. And I wanted to show you this because in a second I'll show you this on hardware. So what is this predictive sampling? It is literally the simplest possible shooting method. Okay? So you've got a nominal, and at every planning iteration, you roll out the nominal, you roll out noisy version of the nominal, pick the best one, call that the nominal. That's it. That's the method. It's like, it's not even a method, it's a baseline, right? It's like if what you're doing is not as good as this, then throw away everything, start again. Okay, because this is like a line of code, this thing, right? There's nothing here. And how could this possibly compete with Newton's method, or with proper optimization, anything that is actually, that was designed for decades or hundreds of years sometimes by serious people, right? Why does this work? Why should it work? It shouldn't work. And there's two answers. This is not the answer. This is the wrong answer. The wrong answer is that sampling is very fast. It's about, I don't know, okay, it's 8 times faster than ILQG. But this shouldn't matter, right? 8 times faster is not supposed to make such a big difference. Here, by the way, you see, right? So this slice, this rollout here is equivalent to the entire. So sampling is just one tiny slice of ILQG. But that doesn't answer, right? 8 times faster is not the right answer. And I think this is the right answer. The right answer is that predictive control is not really optimization. Predictive control is doing something else. Because optimization is about finding the minimum. And all the algorithms that you learned in your optimization class are designed to go to the minimum. But when you're doing predictive control, you are actually trying to do something much weaker. You have a much weaker constraint. You don't care about the minimum. You're trying to stay in the basin of attraction of the minimum within a shifting landscape. Okay, the landscape is shifting under your feet, and all you care about is staying in the same valley, as it were. And it's a much weaker requirement, and it's actually quite different. And I think we need a new metaphor for this. Okay, this is not mountain climbing, this is surfing. Okay, you're just trying to stay between these two waves. You don't need to reach the bottom or the top. It's just about staying in the basin. Okay, so what is MJPC good for? It's great for task design. Like, even if you do RL, you should start with MJPC just to tweak your reward functions, because it's so easy and fun. Data generation, we're using it now. Did I add one of those videos? I'm not sure I added one of those videos, but I don't have much time. We're using it now for data generation. It's fantastic. For example, the thing that you could do is you could take trajectories from humans. For example, humans doing some manipulation and maybe they're motion captured. A lot of people are into measuring what humans are doing now and imitating them. Well, okay, do that. But now take this data, use predictive control to make a tracking controller around this trajectory, around what the human did. And now in simulation, you can perturb. And you're getting these beautiful things, right? So if the human, lifted a glass bottle, now I have the same trajectory, but with someone pulling on the glass bottle, and the hand reacts. So you get all of these reactions that you get in predictive control, you get them in your data set. So you have a data set of perturbation, rejection. It's incredibly powerful, and I hope we're going to do something really fun with it this year. MVPC is just great for predictive control research. I'm going to show you some people. I don't know if they're here, but quite a few people have already contributed to the repo and are doing really cool stuff. And of course, MGPC is just an example of how to use MuJoCo. And I think in a few hours, Emma will give you another example of how to use MuJoCo. But MuJoCo is basically, it's a very low-level tool, and you can use it to build other tools, right? Because it includes all of this GUI framework, which is very easy to use. So in summary, MGPC is an open source interactive tool for predictive control using MuJoCo. It lowers the barrier to entry. Anybody can do it. Like I said, I'll show it on your laptop. And sampling is often, sometimes better than derivatives. And now I have just a sequence of videos that I want to show you of stuff that happened in MJPC. I'm going to show you a very quick, I don't have much time, so so this is like our quadruped task. Let's scroll forward to some more fun stuff. This is fun. Look at this backflip. How cute is that? You can do a backflip. You can do, and look at the GUI, right? I just select front flip and click the flip button, and it does this. Biped mode. The reason I want you to show you this especially is because in a second I'm going to show you this on hardware. Okay, and we've got some gates. Let's show some gates. Yeah. So here, because we talked about in the talk before me, we talked about, so the contacts are not prescribed, but there's like a hint describing the gate. So there's like a hint that says, oh, you probably want to lift this foot, but I'm not, there's no hard clamping, there are no constraints. What are we now? This is canter. And I think if we go a little bit faster, it will auto switch to gallop. And this is very simple logic inside the task definition. Like the whole thing is very, very easy to read. It's like 100 lines of code for this entire task. All right, next. This is the tracking that I told you about. So this is tracking, this is full body humanoid tracking. So you take some mocap data set. This is the AMAS data sets. That's the red dots. And then you ask the humanoid to track it. And of course, you get a physically realistic trajectory in as much as this funny model is realistic. But everything is like fully actuated. It's not just kinematic. So this was the tracking that I told you about. We're now doing this with, this is so cute. So this is from the Royal Veterinary College. So these are, MuJoCo as a side gig is a really good biomechanics simulator. And this is like a full muscle. I don't remember the numbers, but they're crazy as they are in biomechanics, like 200 muscles or something like that. So this obviously doesn't work in real time. This is slower than real time, but faster than RL. And this is solving a Rubik's Cube in real time. And when I say solving, I don't mean figuring out the solution. I mean unscrambling. Okay, so, and this is again just with the silly random sampling algorithm. So it's basically like inject noise into your hand and pick the thing that unscrambles the cube. And it's quite shocking that this works, but it does. So there's something about these sampling algorithms that you need to be lazy enough to try them in order to discover. And if you're not lazy enough, you won't succeed. And now I'm going to show you some recent stuff. Sorry, this is just videos. So these are some people, you can talk to them downstairs from Caltech that did the in-hand reorientation on a real robot. It's so cute, come on. How can you not love this? Let's give it 2 more reorientations. And we did last year, we were trying to show NVIDIA that Mujoko is good on GPU. So we did this pancake flipping on GPU. And then 2 months ago, these guys used MJX. So this is high width batches on GPUs. And they transferred it to hardware, which is very impressive. And finally, this is a little collaboration that we have with the Manchester lab. So here you see 2 time synced real-time recordings. This is a screen recording of Mujoko, screen recording of the robot. And let me just get to, in a few seconds, we're going to see the biped task. And then I think that's my, is that my last video? I think that's my last video. And then I'm done. Look at that. How cute is that? Now it can also get up and sit down, you know, like it can do the switches already, if I remember correctly. It took them about a week to do this. Of course, they already had an estimator, which is why we asked them if they wanted to do this in the first place. But estimation isn't that hard. You just need to try it. Oh, okay, I wanted to show you this. So this, I don't think any derivative-based method will ever succeed in doing this. This is a handover task. So you see, you need to bring the box to the target, but the only one hand can reach the target. So it needs to figure out how to hand over the box from one aloha to another. And it's quite creative and it usually succeeds. And now let me show you the most impressive. This is kind of in-air insertion. So both hands need to pick up. Did we miss the first insertion? This is quite hard. Like it needs to keep trying and trying until it succeeds. They need to pick it up and do the double insertion mid-air. This is at, you can see at the top, it's at 20% real time. So I sped up the video. Actual video is a bit slower. And you'll see in the end it succeeds. I think I missed the first success. Oh, here we go. Click. You see, so every time it succeeds, these guys jump away and it keeps trying and keeps trying. This is a great, so even if you're not using MPC, this is a fantastic data set, right? Just take this data set and, you know, I don't know, do RL, do BC, do all the things that you do with data nowadays. But it's really cute. And I think this might be my last slide. I'm done, right? I don't have any more time. Okay.
Maybe one more question. Okay, Emo? Okay. Oh, Fabio.
Question about sampling, right? So at the moment you're doing Gaussian sampling. Is there anything else you think you could do to improve the performance by sampling?
I think anything that you do will improve the performance. For example, the Caltech guys use a modified version of CEM, which is like Gaussian ++, right? It's like a slightly improved. Do I have another video? I'm just checking, sorry. Yeah, we also have estimators. We can talk about it a little bit. But yes, it's very easy to improve on sampling because it's literally the simplest possible thing. So yeah. Najib?
Okay, Emo.
Yeah. Can you say something about how performance changes with the number of samples you can record per hour?
Ooh, it improves. The answer is it's super problem dependent. I can't, if I had a nice summary of saying it, I would tell you.
Nice to record the data and show it for like 10 different benchmarks. So people know.
Yeah, no, that's a nice idea, yeah.
How does your algorithm scale with the number of objects? Do you try with many objects and try to?
I mean, I don't think, you mean just objects in the scene or objects that I need to touch?
Touch and, you know, basically.
So this is a question about how Mujoko scales with lots of objects.
Also, you need to, find some functions in different objects and I don't know. Yeah, it's actually.
No, I think the cost is going to be cheap. So the general answer is it scales like your simulator scales.
I'm asking because I want to see, do we need then Haskell motion planning kind of thing, like the way Mark does it, or, having logics and define predicates, or no? You think we should just go with it?
No, I mean, look, what Mark did was amazing. So like there's something there. What can I say? Like we have this funny landscape with like a jungle, and we have this hill that this thing works, and that hill and that thing works, and this unexplored region in the middle. Like I don't know how to combine this high level reasoning like Mark did and this stupidity that just happens to work. I don't know, but somebody should at least try.
So let's stop here and thank again, Yuval.